Hello. Today's video involves the second derivative, what that tells us about the original function and how we can use it. First off, second derivative of the original function. First off, if my original function looks something like this, then the second derivative, f double prime of x, is going to be less than 0. And we would say that this is concave down. If my original function looks like this on an interval, f double prime of x is greater than 0, and so this is the original function, f of x then is, we say, concave up. The way we can use this is, if I have a critical value where the slope is 0 at some value, let's call this x1. So f prime at x1 is 0, critical value where the derivative is 0, and my second derivative is negative, then this implies that since this f of x is concave down, this means that f has a relative max at x1. If I have a nice smooth curve here with, let's call this x2, when my derivative is 0, f prime at x2 is 0, my function is concave up, this would mean that f has a relative min at x1. At x2. So we don't have to do a sign table in these kind of situations. We can use the functional value of the second derivative. The first derivative function can tell us, the graph of the first derivative function can tell us about the second derivative, or the concavity of the original function. Let's suppose that I have a function that looks like this. Let me put it in an axis. This is the graph of f prime of x. And I want to, just like we used the graph of f prime to tell me where the derivative, where the original function was increasing and where I had relative max and relative min, I can use the graph of f prime to tell me where f of x is concave up and also concave down. Concave up, remember, this means f double prime of x is positive, which means that the derivative of the first derivative is positive, or the slope of the tangent lines are positive. Notice that occurs to this value, which I'll call x1, and that occurs over on this side from x2 on. And so we would say on the intervals from negative infinity to x1, my function is concave up, and also from x2 to infinity. The original function is concave down when the derivative of f prime of x is negative. That would occur in this middle section here. And so this would be on the interval from x1 to x2. Where my function changes concavity, in this case at x1 and at x2, we get what are called inflection points. Inflection points where the graph of f of x changes concavity, which in this case are equal x1 and x2. Okay, let's look at some examples of functions and using what is called the second derivative test, what I kind of outlined, to determine relative max and relative min. I will write the second derivative test out first. Second derivative test says if f of x has a critical value at x equal a, where f prime at a is equal to 0, a critical value where the derivative is 0, and three parts. Part 1, f double prime at a is less than 0, then f has a relative max at x equal a. This is the situation that I described, like that. Second part, and f double prime at a is greater than 0. Then f has a relative min at x equal a. Again, the picture, the picture looks something like this. This is my value a. And the third part, and f double prime at a equals 0, or f double prime at a does not exist, then we can't use the second derivative test. You must determine relative max and relative min from the first derivative test, what we talked about previously. Okay, let's look at a couple examples where we can use the second derivative test. Suppose I have the following. F of x equals 2x minus 4 square roots of 2x minus 1. The domain, x is greater than or equal to 1/2. Remember, you can't not have a relative max, relative min at the end point of the domain, so we don't have to worry about x equal 1/2, but let's see what happens. F prime of x, 2 minus 4 times 1/2. Remember, this is 2x minus 4 times 2x minus 1 to the 1/2. 1/2, 2x minus 1 is a negative 1/2 times 2, or 2 minus 4 over the square root of 2x minus 1. This derivative does not exist at 1/2. Again, we don't have to worry about that. That's the end point of the domain. We do need to know where this derivative is equal to 0 to find my critical value. And so we get 2 square roots of 2x minus 1 minus 4 is equal to 0, or 2 square roots of 2x minus 1 is equal to 4. The square root of 2x minus 1 is equal to 2. 2x minus 1 is equal to 4. So 2x is 5, x is equal to 5/2. This is my critical value. This is where the derivative is 0. So now we need to figure out what happens at this value. And I want to use the second derivative test, which means I need the second derivative, f double prime of x, The derivative of 2 is 0. I'm going to use this form here. Just get rid of these completely. I get negative 4 times negative a half 2x minus 1 to negative 3 halves times 2, which gives me then, and these kind of reduce, 4 over the square root of 2x minus 1 cubed when I rewrite it. Now, the square root is always positive for any value other than what makes it 0. And so at 5 halves, this result is positive. I don't really care what the value is. All I care about is that when I plug in 5 halves, my result comes out to be positive. Therefore, my original function is concave up, which means I get a relative min at x equals 5 halves. One more example. I'll leave that up for a moment. Suppose I have f of x equals the natural log of 2x plus 3 plus 2 over x. The domain in this case, x is greater than negative 3 halves, x not equal to 0. For the two pieces of this, my derivative, 2 over 2x plus 3 minus 2 over x squared. The derivative doesn't exist at negative 3 halves and 0, but they aren't in the domain, so we don't have to worry about them. We do need to find the critical values. So I will set this equal to 0. 2x squared minus 2 times 2x plus 3 is equal to 0. 2x squared minus 4x minus 6. I can factor out the 2 first. And this factors nicely, which is good. And I get x is equal to 3 and negative 1. Both of these are in the domain. That's why it's important to know what the domain is. These are critical values. So now I will apply the second derivative test to those critical values. I need the second derivative. Let me rewrite this as 2 times 2x plus 3 to the negative 1 minus 2x to the negative 2, make it a little easier. You don't want to use the quotient rule when you can use the power rule. The derivative is negative 2x plus 3 to the negative 2 times 2, chain, plus 4x to the negative 3, or now I'll rewrite it, negative 4 over 2x plus 3 squared plus 4 over x cubed. And let's check our values. The second derivative at 3 is negative 4 over 9 squared, which is 81, plus 4 over 27, which is negative 4 over 81 plus 12 over 81. And this therefore is positive. I don't really care what the actual value is. It's 8 over 81, but that's kind of irrelevant. What matters is it's positive, which means I get concave up, and so I get a relative min at 3. The second derivative at negative 1 would be negative 4 over 1 squared, which is 1, minus 4. This obviously is negative, which means concave down, and so therefore relative max at x equal negative 1.